Good morning, friends. We have been discussing about aerofoil for the purpose that finally at the end of the day the lift generation is to be through a proper wing. When you talk about lift to drag ratio to make our airplane efficient aerodynamically, again wing plays a very important role. When I want to balance the aircraft, you will see that there also selection of airfoil plays an important role. Why important? Perhaps the most subtle role. Unless we handle it correctly, finally we find the design is not a good design. If I just do a summary of whatever we were discussing, typically in my lectures I call this session as Man Ki Baat, right? I go back, I check the videos, I find, oh, at this point I have just gone very fast, or perhaps I have given too many informations. Giving too many information is not right way of sharing knowledge, right? So that is why I always create one session where I cover it under Man Ki Baat, where basically we do revision and try to make things clearer for my mistake, which I have done during my recording, whether in terms of writing something wrong or going fast on a particular concept where I should have been a little more slower and I should have given a more stress. So I have just given a thought in the night and try to summarize. What we are doing is airfoil or aerofoil selection, and we are preparing ourselves, whether we know at core level what is an aerofoil, what are its characteristics, what are its parameters which decides the desired characteristics. And we have seen that especially the aerodynamic characteristics mostly can be covered through knowing what is the CLmax, what is the alpha stall, what is CMAC, maybe whether flow is laminar, you want over most of the part of the wing, etc. Right? If I take this CLmax, we know that most of the time when the airplane will be flying, it will not be flying at CLmax. But why we are giving so much stress on CLmax? For simple reason that Vstall, which we understand is the minimum speed at which the airplane can maintain a level unaccelerated flight, is given by 2 W by S rho CLmax. So if CLmax is higher, then your Vstall is lower. A Vstall lower has a lot of advantages, that your engine power requirement reduces. And also, you know, V touch down or V take off, they are almost like 1.2 to 1.3 times V stall. So if V stall is less, then V take off and V touch down is also less. So you have direct implication on the engine power selection. Right. There's another thing for a designer. You could see if you are taking off from a high altitude, maybe Leh, Ladakh, some place like that the density of air will be lesser compared to sea level density of air. So there also you see that because of high altitude, because rho goes down at high altitude, your Vstall has a tendency to be more than Vstall required at sea level. So how do I compensate that? Because anyway I have to take off from Leh. So if I have a larger CLmax, then I can manage that much of Vstall which my engine power can deliver, right? So this is one way of looking why do you want CLmax. Please understand, for an aircraft, takeoff and landing is very, very crucial. Mostly when you are flying at CLmax, let us say I am flying at CLmax, which is theoretically you are close to alpha stall. So imagine I'm coming for landing, and because of some ground effect or ground upward wind, the local angle of attack suddenly increases. Then you are actually falling here. So that's very, very bad way of operation. You do not operate at this point. Why you are operating at this point? Because you want high CLmax. This is CL. So instead, if you have something, the CLmax is higher because of aerofoil or because of other considerations, you can as well fly here during takeoff and landing. So you are safe. So there is a reason why you want to operate at high CLmax. So what we do, by selecting an aerofoil, we try to see what is that aerofoil shape for which I will get CLmax higher. Typically, you will find for conventional aerofoil, symmetric and all, the CLmax is almost saturated at 1.2. Then what we do? We say, okay, you introduce camber. We are introducing camber, so there is a camber line. By introducing camber, you are actually increasing further your CLmax. That is where the camber part came. So we introduce camber to increase CLmax. But note one thing, the moment I am introducing camber, this portion, that is at alpha equal to 0, you are also getting CL0. So this also increases. And you have to be careful about what is the effect of this in terms of balancing the aircraft. We will be talking about those. Alpha stall and CLmax goes together. And let us say you have an aerofoil where maximum by doing this optimization, that if I increase camber, CLmax increases but stall also reduces. So you say, okay, at the most I can get CLmax around 1.4 or 1.5, but from Vstall requirement during takeoff and landing, you will be happier if CLmax is around 2 or 2.5 or 3. Then what do? Then the point CLmax, I increase not only through aerofoil, which is already basically present and already designed, so I use high lift devices. We'll talk about high lift devices in detail. It essentially means that some portion of this is put down 10 degree, 15 degree, so effectively changing camber locally at that point, and you have got a higher CLmax. I have written here CMAC. The moment there is a camber, as you introduce camber, and you know that if this is the camber I have introduced, then the lower portion resultant force will be in this direction, upper one in this direction. They don't pass from the same point. So about the aerodynamic center, when you want to shift these forces to aerodynamic center, it will have CMAC negative. That is one challenge you have to handle, CMAC negative. More and more camber you are giving, CMAC will become more and more negative. What is the issue of CMAC being more negative? Let us see that. Suppose this is the wing and this is the horizontal tail. I want to balance this airplane, that is, balance this airplane in air. should go like this. And let us say this is the AC, and somewhere you have kept, let's say CG is here, or for simplification let me put CG is somewhere here. That is, I am writing a case where AC of the wing is ahead of CG. Right? Now what will happen, you see, as I give angle of attack alpha, there will be aerodynamic force I can represent roughly. I am just drawing perpendicular to this, which is strictly, it has to be perpendicular to this. Because angle of attack is small, I am drawing it like this. So there will be a lift generated here. This will give a nose down moment at CG. Equivalent alpha, which may not be equal to this alpha, as you know, this alpha tail will be lesser than this because of downwash. So this will generate a force here, lift tail, and I have to ensure that the moment balance is there, that this lift giving moment about CG nose up, this gives nose down. So I have to ensure the lift as well as the distances so that there is a moment balance. But the problem is, once you have a cambered wing, you already have another CMAC which is less than 0. This moment is also there. You have to correct the moment about CG because of lift on the wing, which is balanced by lift on the tail, plus you have to balance the nose down moment which is coming because of CMAC. So if I just throw the wing, it will come like this. So you have to ensure that through tail I balance the CMAC also. But unfortunately what is happening? The CMAC is less than 0, nose down. So any alpha here, it also gives the nose down. So this will not be able to handle CMAC negative. But you have ways of doing it. You know, we will see that we put the tail in a tail negative setting angle, which tries to give force in this direction, which gives a nose up moment. So all this thing you have done in stability and control. What I am telling, the moment you are using a cambered aerofoil, please be careful about CMAC. You should not allow CMAC to be very, very large negative. Then you have to pay penalty, or you have to do a little ingenious way of handling how to do that, right? So this is what I thought I must share, which is nothing new for you. You have done these things. Of course, you know, laminar, etc. flow. You have to maintain typical Reynolds number on the wing, or major part of the wing, so that it is able to generate laminar flow. At the same time, you know, if you want to make a laminar wing, manufacturing is demanding, as well as keeping that wing clean is also demanding, because small particles may locally turn the flow into a turbulent flow, right? Okay. There's another topic I was discussing was T by C, this thickness to chord ratio. Right? And you should know from the discussion what came out was, if I plot CL max by T by C, the trend will be something like this. A particular T by C, generally it is between 10 to 14%. These are the design number, typical numbers, right? You get maximum CL max as far as effect of T by C is concerned. So most are designed low subsonic, you will find they will be operating around this. The moment you go high speed, this Mach number effect also comes, right? Because you need to have a smaller T by C so that you reduce the drag. In turn, you increase CL by CD. So their T by C requirement will be more decided by the Mach number effect. Okay. Similar T by C with drag, as T by C increases, drag also will increase. So let us say this is for 6% T by C, you would expect this is for 20% T by C. Typically, there will be increment based on different type of aerofoil, but you should know that there is going to be a penalty you are paying as you are increasing the T by C as far as drag is concerned, right? Or CD, drag coefficient, is concerned. Then another thing we discussed, which was very lot of time we spent, the critical Mach number. That is that free stream Mach number at which for the first time some part of the or some point on the aerofoil attains Mach 1, right? And if I see T by C versus Mach number, this critical Mach number, MCR, if I point it around, so it will typically it will be something like this. And this region is around 10 to 12%. Typically M critical changes with T by C. This sort of a variation you will find, and this may be around 14 to or not 14, maybe around 20 to 24% T by C. There is a large drop in critical Mach number as you are going beyond 10 to 12% T by C. That is very important, right? Okay. So when you are trying to go for a high subsonic airplane, and if for some reason you want to go for a T by C higher, you know what sort of penalty you're going to pay, right? Either you, if you have no other option, if you're so destined you have to go for higher T by C, one understanding can help you try to give a sweep, but as you give sweep, you understand you are losing lift as well. So these are all sort of a optimization goes on, right? You have to negotiate with all these conflicts. As a typical designer, if you want to just get feel for numbers, you will find typically this zone where your T by C is 10 to 14%. Here mostly for Mach number range of 0.4 to 0.6, 0.7 around that, you will find T by C 10 to 14% or 12 to 14% will be okay. As you go higher speed 2 or Mach 3, you will be approaching towards T by C of 4%, which are generally available and being tested, right? This is the order of magnitude, right? You could see the difference 10 to 12 or 14% to 4%, maybe 6%, maybe 5%, right? Around that. So this is one observation you must have. Also, please understand this critical Mach number and CL have some sort of a correlation, right? Remember when you are having CL, drag the CD will have a unique value for a given CL, right? Okay. So as the CL increases, CD also will increase. So let us see how M critical, typically it varies with rough idea, don't take too much on this. If this is 0.8, this is M critical, this may be around 0.4, 0.3, and these points are, this is 0.1 to 0.4, that range CL, this is. So you have critical Mach number around 0.8. As you go to higher CL, there is a huge drop in the Mach critical Mach number. So you understand if you are flying at a higher CL, your critical Mach number is going to reduce. But if you are operating between 0.1 to 0.4, critical Mach number will be maximum that time, manageable, right? Okay. Then there is another discussion we had on the camber line. So let me write here Man ki baat. One was location of camber, that is maximum camber, right? And magnitude of camber, maximum camber. After all, why you introduce camber? The purpose was to get CL max higher, right? As far as location of maximum camber is concerned, understanding is if it is located 40% of the chord measured from leading edge, the typical number, then general feeling is that it gives good handling qualities. Right. What happens if you move this location of T by C max forward toward the leading edge? Yes, it indeed increases your CL max, partially yes. However, your stalling, alpha stall, reduces very fast. And so, if you are really taking T by C maximum forward and forward, you will find that there is a tendency of the wing to stall abruptly. Right? So that is why you will find with all those data sets, as a designer, roughly 40% of the chord from leading edge, if you are locating the T by C maximum, you can start from the conceptual stage that it is likely to give good handling qualities. Right? These are the experiences I am sharing. These are not numbers which you can challenge in the court. Right? 40 could be 35, 35 could be 37, but it is not 10%. Okay? That way. Another knowledge I want to share with you is, if you see CL versus alpha, and if I am plotting, this is for 40% location, that is maximum, T by C maximum is at 40% of chord measured from leading edge, and another if I draw, this is 15% location. You could easily see that this is from a test data which follows the logic, right? If T by C maximum is forward, the flow will accelerate very fast, right? So naturally it will stall also very fast. You see 50% location, it is stalling much earlier, and it is abrupt also. This is important. Not like this, this is abrupt, okay? Which is not good as far as handling qualities are concerned. And if somebody asks me, I was just checking data set, if I want to know CL max versus T by C, what sort of T by C I should take? Typically you will find around 12 to 14% CL max will be maximum. CL max, this will be the maximum value. Generally you get for low speed, 12 to 14%. Because you know at high speed, T by C vis-a-vis CL max is not that important as drag is important, because finally CL by CD is important, right? So this has to be perceived in that manner. Also you could see how important is T by C. If T by C is increased, then critical Mach number reduces. So if you are designing a high-speed airplane, high subsonic even, so you know, man, T by C, increasing T by C may have advantage in CL max, but I have to give penalty. Critical Mach number will go down. So you have to find out alternate methods, alternate attributes to optimize this, right? Because there may be a conflict, you indeed want T by C to be higher. Right? And also T by C, as it goes down, or if I T by C as it goes up, drag divergence Mach number goes down. This is for high speed. This draws maximum sweat from the designer, because you know that yesterday we defined drag divergence Mach number. There is sharp rise in the CD. So whatever T by C advantage you may be getting, but if it doesn't give you satisfaction or drag divergence Mach number for high subsonic airplane, you say thank you very much, I will find some other way. We have also touched upon something on leading edge radius. I thought I also mentioned this, between radius 4% 6% of chord, not much affected by Mach number. If you see from 0.4 to 0.75, on that Mach, yes, small rise in CLmax is observed, but small. These are just some observation. When you will be actually designing an airplane, we will see the data sheet and we will try to then recall, oh, what is this meaning? Is that happening or not, right? Today I thought I will only do this much. Please go through my lectures and also take some textbook and read the relevant matters, see the data, do Googling. That is the best way to learn a design course, because at the end of the day, we are not sitting together to design any configuration. That is the limitation here. Thank you very much.